Hello and welcome to this lecture. So we've been looking at computing limits, and we saw how you take a limit of an expression, and that expression is maybe it's a rational form. It's got numerator denominator, and now you can push the limit inside, and how we have to watch out for these infinity minus infinity type situations, infinity by infinity, 0 by 0. Then make some adjustments if possible and compute limits. So being able to compute limits is very important. And we're going to take a next big step in computing limits, where it'll be important to know by looking at the sequence and studying it whether or not the limit exists before you can start computing. You might wonder how it's useful. You'll see when I show it to you, you'll understand. If you know from the way the sequence is being defined whether the limit exists or not, then you can compute that limit using some very nice simple tricks like taking limits, etc. This will become easier. Okay, so but you should know it exists. So how do we do that? For that, this monotone convergence theorem is something very useful. It's we won't sort of rigorously prove it. In fact, it's sort of one of those assumptions about real numbers. It's not too much. There's not too much of a proof as such, and there's lots of uh, statements about whether it's a proof or whether it's a theorem or whether it's an axiom and things like that. We'll just call it a theorem and we'll move on. Okay, so this is the important fact. It's a very, very powerful property of the real numbers. It's basically, it says if you have a sequence which is non-decreasing, which means you can think of it as increasing if you like, okay, an increasing sequence that is bounded above. Okay, notice these properties. If you remember, if you recall a little bit, for sequences we had these properties. Is it bounded above, bounded below? Is it monotone increasing? Is it monotone decreasing? Is it monotone non-decreasing? Is it monotone non-increasing? You might remember this terminology we had. Basically, non-decreasing, think of it as it does not decrease, which means it could increase, right? So, or stay flat. So that's what that sequence does. What this monotone convergence theorem is telling us is a non-decreasing sequence that is bounded above has a limit. Limit exists and it's finite, right? So this is a powerful property. Same thing below also. If you have a non-increasing sequence, it's either falling or staying flat, but it has a bound below. So it cannot go off, diverge off to minus infinity. But then if it does that, it has a limit in the real numbers. So the real numbers have this fantastic property. Like I said, it's more or less an assumed property of the real numbers. And once you have this property, a lot of limits can be very, very nicely calculated. And you'll see it's sort of consistent. It works quite well. So this is called the monotone convergence theorem. Hopefully you understood the statement of the theorem. So if I'm given a sequence and I cannot compute its limit, but I want to know whether limit exists or not, all I have to check is whether it's monotonic and it's bounded. And the correct kind of combination, right? If it is bounded above and it is sort of monotonically increasing, then it has to have a limit. If it's bounded below and if it's monotonically decreasing, it has to have a limit. Okay, so that's a fantastic property, and we'll put it to use in our computation of limits. Okay, so let's see how this works with a few examples. I'll just go through these examples. We've seen these examples before. Just to reiterate, we'll go through these examples. Here's the sequence: a n equals 1 by n. We already know a limit exists for this. We've computed the limit using the epsilon definition. Now, without even computing it, can we know ahead of time that a limit will exist? It turns out it's true, because this sequence is a decreasing sequence, right? It is the non-increasing sequence. It keeps decreasing. You remember the plot of this I've showed you, and you can also see 1, 1 by 2, 1 by 3, 1 by 4. It is always decreasing. Every value is below the other value, and it is bounded below. Bounded below meaning it has a lower bound of 0. Okay, it has a lower bound of 0. All the values in the sequence are above 0, and it keeps on falling. So by the MCT, this sequence has a limit. Okay, whether or not we can find it, that's different. We've already found the limit for this, but still we know that a limit exists without even finding what the limit is. Okay, so here's another sequence, minus 1 per n. This one is bounded below, right, by minus 1, but then it is not monotonic because it keeps going minus 1 plus 1 minus 1 plus 1. So technically MCT does not apply. We also know that this sequence does not have a limit, right? So here's another sequence, 1 minus 1 by n. Here if you look at it, it starts at 0 And then as n increases, this sequence is also increasing. So here is a monotonically increasing sequence. Okay, for every n, as n becomes higher and higher and higher, here are a few examples shown here. You can make a plot also if you like. This is increasing and it is bounded above. It is an increasing sequence and it is bounded above. Bounded above by what? By 1 or 2 or anything else. Okay? Many bounds are there, but 1 is sort of like a nice upper bound that you can have for this sequence. Of course, 2 is also an upper bound. If you want a very easy bound, you can do things like that. So you see there is an upper bound and it is an increasing sequence. So it has a limit by the MCT. Okay, so it's quite easy to figure this out. I don't have to do the epsilon calculation to find the limit and then show that the limit is finite. I already know that there is a finite limit for this sequence. Okay, here's another final sequence minus 2 power n, and you see this is not bounded, so MCT does not apply. Even though it is monotonic, it's not bounded. It's not bounded below in the correct direction. Okay, so hopefully you see different sequences MCT may apply, may not apply, but wherever it applies, you know that there is a limit. Okay, so how do we use this? I'll show you how to use it. It's most commonly used when there is a recursive equation that defines the sequence. MCT is very powerful in those situations. You can wonderfully use it to establish the existence of a limit, and once you establish the existence of a limit, there is a very easy trick to compute the limit if you have a nice recursive definition for the sequence. So here is an example. We saw earlier this geometric progression sequence, right, r power n, and I'm going to take the specific case where r lies between 0 and 1. Okay, if r is greater than 1, this geometric sequence is going to diverge to infinity, plus infinity, right? If r is between 0 and 1, we saw from the plots it seems to be converging somewhere. So let's investigate that situation. If you look at this, this is the sequence r power n, and that's 1 r, r squared, so on. Okay, 1 r, r squared, and so on. This sequence has a very nice recursive definition, right? A0 is 1, an plus 1 is r times an, right? You're multiplying the previous value of the sequence by r. So this is the geometric progression. You can see that this has a very simple lower bound, an greater than or equal to 0, right? Every value here, since r is non-negative, positive, I'm multiplying by r, every value here is greater than or equal to 0. And in addition, this is a decreasing sequence. Why? Because an gets multiplied by r, which is strictly less than 1 and greater than 0. So this multiplication is going to make this r times an smaller than an, and an plus 1 is less than an. Okay, so it's quite an easy proof to do. So you see this has got a lower bound and it is decreasing. So by MCT, I know that there is some limit for this sequence, and let's call that limit L. I don't know what that limit is. Maybe one can easily guess, but still, let's say assume I know by MCT that the limit exists and I don't know what that limit is. I'll call it some L. Okay, but the crucial fact is limit exists. Once I know limit exists and it's finite, I can do very many interesting things with the recursive equation. Okay, so here is the most important trick that's going to come up, finding limits. I can take limits on both sides of this recursive equation because I know limit exists and everything is going to converge to some nice thing. So I can take limits on both sides of this an plus 1 equals ran. So this is a powerful and simple technique. And if you do that, you'll notice what happens here. Limit as n tending to infinity, an plus 1 is r times limit. I know limit goes inside scalar multiplication, limit as n tending to infinity. Now what is this guy, by the way? This guy we know is L, right? Limit as n tending to infinity an is L. What do you do with this fellow? Limit as n tending to infinity an plus 1. Okay. When you look at it, some people get a little confused by this. They think it is something else. But guess what? I mean, n is infinite, n is going very large here. I'm looking at the same sequence, right? an plus 1 is the same sequence as an. There is nothing different between an plus 1 and an. It's the same sequence, just shifted by 1, you know. How does it matter in the limit? The limit, I'm looking at very large values of n. So all these things don't matter. So an plus 1 also has a limit of L. Okay. So this couple of crucial facts, the fact that you can take limits on both sides of a recursive equation, and the fact that these an plus 1 and an are actually the same sequence asymptotically, and when you take limits, they end up being the same value. So you put L equals R times L, and R is strictly less than 1. You can pull this to the left side. You will get 1 minus R times L equals 0, which means L is equal to 0. You have established that this limit is indeed equal to 0. Just check this computation once again. Make sure. A lot of people will cancel L on both sides and say R equal to 1. You shouldn't say that. Shouldn't do that, but L could be 0. If L is 0, you can't cancel this. So you keep L, push this to the left side. So you take common L common out, L times 1 minus R equals 0, and R is strictly less than 1, right? So that 1 minus R can be cancelled. So you get L equals 0. Okay, pay attention to this method. It's a very nice and simple method. So using this, we have managed to show that limit as n tending to infinity, R power n is equal to 0 for 0 less than or equal to R less than 1. So notice how this method is so simple and elegant and doesn't use these epsilon definitions, and you could use epsilon definition here also, I'm not saying no, but it doesn't necessarily use all those definitions. Just directly gives you a very simple derivation for how that bound, how that limit has to be equal to 0. So you could have also guessed it in this case, as if you take, like, for instance, R is 0.5 and you keep raising it to higher and higher powers, eventually it will drop down to 0. It's very intuitive and physical and simple, but this one is like a nice clear math proof for the whole thing. So you may want to recall that if R is greater than 1, limit as R power n is infinite. It diverges to plus infinity or converges to plus infinity, as some people say it. So this limit is infinity, and this guy is 0. Okay, so hopefully you're convinced that this MCT seems like a very interesting tool, and wherever there is a recursion, maybe we can use MCT to our profit. And this is a crucial idea, and I'm going to use it now that it has worked for this R power n, which is a simple sequence. I'm going to try and use it for more complex sequences. For instance, the root 2 sequence. We have our wonderful root 2 sequence, which is a0 some value, and then an plus 1 is an by 2 plus 1 by n, right? So this is our root 2 sequence. Now I'm going to claim without proof, that this is monotonic and bounded. This is very important. I'm going to claim monotonic and bounded, as in monotonically. I believe this is what's going to happen if you put 2 here, like 2, 1 plus 0.5, so it's 1.5. If n equals to a1 is 1.5 and so on. So this is a monotonically decreasing sequence, and it is bounded below. Okay, so this is two things which you can verify graphically quite easily, and it turns out you can also prove. So in this course, I'm not emphasizing those kind of rigorous proofs very much. I will encourage you to do it, and if you find a proof, if you find a rigorous proof for monotonic and bounded property of this sequence, please post it on the forum, and we'll all benefit from that. I would thank you for that if you're interested in such stuff. But if you can just plot the graph, and if you're happy to see that it's monotonic and bounded, we can proceed as well. Okay, so this is slightly more applied course than a pure theory course. So by the MCT, the limit exists. And we will suppose, let's say this limit of this an sequence is actually L. Okay, once I know limit exists, I can do my wonderful trick of taking limits on both sides of the recursion. And when I do that, I'll get this limit an plus 1 is limit an by 2. So now I know limit is well behaved inside an expression, right? This is just a simple expression, and then plus 1 by limit n tending to infinity an. So I just take limits on both sides, and then I have this wonderful equation involving L, which is L equals L by 2 plus 1 by L. Then I push this to this side, L by 2 equals 1 by L, L squared equals 2. Okay, so I have proved using this wonderful MCT that this sequence, which I've been calling the root 2 sequence all the time, indeed converges to some L, which when squared gives me 2. Okay, which means what? That this limit can be called square root of 2. This L can be called the square root of 2. Okay, so remember the lot of things I told you about how square root of 2 is actually irrational. It cannot be written as p by q for any rational integer p, integer q. You cannot write that. So however, if you look at a sequence of rational numbers and look at the limit, that limit when squared can become equal to 2. This is what I've proved for you. So limit of rational numbers can do more than what only rational numbers can do. right? So these are sort of important ideas about numbers to get into your head, sort of mathematical ideas. So you have rational numbers. One of the limitations of rational number is there is no rational number which when squared is going to give me 2. Okay, but I want root 2. Why do I want root 2? I want root 2 for various things. I mean, you can think of a right angle triangle with 1 here, the length there is root 2. I want root 2, right? I want to have a number which I can construct which is root 2. So that's where these limits of sequences of rational numbers come in. So even though rational numbers do not have a root 2, if you take a sequence of them, carefully constructed sequence of them, and if you look at their limit using this limiting definition, that limit when squared can become 2. So this limit cannot be a rational number. It will be some other number, and that's an irrational number which we are going to call as root 2. Okay, so you can proceed like this. So this is sort of a mathematical way to think of this, but you can see that the MCT gives you fantastic tools to get to these kind of numbers. Okay, so what we did with 2 to get the square root, right, we can do with any other number b. Okay, so let me show you. Here is some other real number b. Some real number b is given to me. I want to find a sequence which maybe goes to square root of b. So notice what I've done here. I've done a little bit of trick. You can go back here. This is my root 2 sequence. So instead of this 1 by n, 1 by an, right, so an by 2 plus 1 by an, I've replaced it with b by 2 an. Why this? How do we derive this? Is there a meaning to it? This is actually called Newton's method for square root. It goes back to Isaac Newton. I'll have more to say about Isaac Newton later on. So many people, I mean, he's called the father of calculus. So all of these things go back to him in a very strong way. So this one, we will see much later on why these kind of formulae, where they come from. But for now, take it from me that this is a sequence. An plus 1 is an by 2 plus b by 2 an. And this sequence, if you start it off correctly, maybe this course at this point, I can't tell you how to start it off correctly. There are several good choices. You can pick any choice and try the graph, and you'll see for some choices, clearly it will be, for many choices, it will be monotonic and bounded. Okay, so this monotonic and bounded, once again, I'm not going to prove. So these are slightly more difficult to prove, and you can prove them for different ways, and you can investigate how to take the first value. There are a lot of books that will tell you how to do this. If you do that, then by MCT, this limit will exist. Okay, so there is a bit of a gap in my proof, but anyway, I'm going to assume monotonic and bounded. So when this sequence becomes monotonic and bounded by a suitable choice of a naught, then this limit will exist. And guess what happens to this limit? This guy L, if you now take limits on both sides of this recursion, you're going to get L equals L by 2 plus B by 2L, and you do this manipulation wonderfully, you get L squared equals B. So this limit, when squared, is going to give me B, whatever B may be. Okay, wonderful, isn't it? So this is like a way to get towards any square root of B, right? So this is not just root 2, you can do for any square root. In fact, not just square root, you can do for any rth root. I want rth root of B, as in I want a number which if I raise it to the power r, I get B, right? That is B power 1 by r, right? If I raise this guy to the power r, I should get B. Okay, that's my question here, an rth root it's called. Okay, not square root, rth root. It turns out for that, here is the recursion. Okay, once again, we will see later on, this is a standard method called Newton's method, and that's how I've derived this recursion. We'll see that maybe later on, but it turns out such a sequence, if you start off with a good value, it could be monotonic and bounded. Okay, so it's going to be like that. And once you have that kind of value, in many cases it will be, it's quite easy to find this. By the MCT, limit will exist, and I can take limits on both sides of this, assuming that the limit is L. When I do that, and do the same process and simplify, guess what I get? I get L power R equals B. Okay, so this is an important thing to remember. There is a sequence of rational numbers which will converge in the limit to the rth root of any real number B, and that I can just compute in this fashion. So maybe I should be a little bit careful here. See, if B is a rational number, I can do this as a sequence of rational numbers which are going to converge. Okay, in fact, if you think of B as a real number also, you will get a sequence of real numbers which are converging to B. So it's a little bit more complicated, but let's just keep B as rational for now, and then you see that the rth root can be found quite easily. Okay, notice how the MCT is enabling that. Okay, so what else can we do with recursion? Supposing if you look at in general a recursion, a1 is some value, a1 is some value, and then this an plus 1 is given as some expression involving an, right? So these are recursions, and we are seeing that these recursions are really powerful, and MCT is one mechanism to analyze a recursion to see if some convergence happens and all that. So maybe we should sort of look at it in general and how to do it. This course is too early a course for you to see this in detail. You'll see later on in your courses these ideas will take shape. But for now, let's just see what happens in general with recursions. Okay, how do you start understanding a recursion? What I do, what I would advise you should also do, is to first compute a few values. Right, you're given a recursion, just compute a few values. How hard it is to compute, right? So compute and see what happens, and definitely plot and check. Get a stem graph, see what happens to it. Maybe change the initial value, see what happens to the recursion, and if possible, you prove things about that recursion. For instance, you may want to prove a monotone property. You may want to prove a bounded property for this sequence that comes from the recursion for particular starting values. Okay, so if you can prove all that, then you're in business, right? You can ask a lot of questions and you can do a lot of things. Maybe, right? If you're really lucky, it could be bounded, it could be monotonic in the right way, monotonically increasing bounded above or monotonically decreasing bounded below. MCT may apply. If MCT applies, then you're done, right? So you take limits on both sides of the recursion and hopefully you can solve for the limit in some reasonable way. So more or less, that's one direction. But in case that doesn't happen, quite often that won't happen also. If it doesn't happen, then you have to ask yourself a lot of these other kind of questions. Is it unbounded? Is it going to go off to infinity somewhere? Does it diverge, or does it have no limit? Is it going to be going oscillating back and forth between multiple points, and there's no limit as such for the entire sequence? Okay, so all these questions you have to ask about the recursion, and then you may get a situation where limit is either plus infinity, minus infinity, in the sense that it either converges, diverges to plus infinity or minus infinity, or the limit may not exist at all. Okay, so this is how you solve for recursions in general. Okay, so this hopefully gave you a good idea as to how this monotone convergence theorem is used in computing limits. So having learnt this, let's quickly go through a few examples, not a few, there are 12 of them, okay, and to see how the limit is. So first ones I'll go through a bit quickly. Maybe the recursion part I'll spend some time and do in slightly more detail. Okay, so what about 1 by 2 power n? What is the limit? Okay, so this we have seen already, right? So this is like half power n, right? 1 by 2 power n is the same as half power n. It's 0.5 power n. We already saw this. R power n, when r is between 0 and 1, that's going to go to 0, right? So this limit is 0. 1 by 2 power n is 0. Okay. Here is the second problem, 1 plus 0.5 power n. So if you take limit, what will happen here? This is just, just standard limit rules. Now that we know 0.5 power n limit, you can just take limits. Limit of the sum of 2, so it is just 1 plus the limit of this guy, and that is just 0. So this limit will be 1. Okay, see how easy it is. I mean, once you know the limit for 0.5 power n, you can just powerfully use it and get around and do things. Okay, so that's 1 plus 0.5 power n, that is just 1. So what about this one? I put a rational function with this 0.5 power n entering the picture, and you see 0.5 power n will go to 0, 0.7 power n will go to 0. So in the limit, this fraction will go to 1 by 2. Okay, so 1, 2, 3, very easy to do. You just, now that you know the limit for r power n as when r is between 0 and 1, you simply use it in rational expressions directly. Okay, 4, 5, 6 is also similar, except that I've twisted it around a bit, and instead of putting rational numbers power n, I seem to be putting 2 power n, 3 power n and all that. Okay, so how do we do this? Let's try the first one, 1 by 2 power n plus 3. The fourth problem is limit as n tending to infinity 1 by 2 power n plus 3. Is it 1 or something else? Yes, 1. So on the face of it, it looks like what is this 2 power n? It's I don't know what to do, etc. You may get confused by that. But then again, you know what's going to happen to this, right? So what should happen to this? See, this 2 power n plus 3 is going to be unbounded. It will grow to very large values for large n. So if you do 1 by that, this should tend to 0, right? But how do we neatly write it down? So here is one way of writing it down. So this is 1 by 2 power n. I'm going to divide numerator and denominator by 2 power n. Notice how I've done that. The reason, once I do it, I see that I will be in familiar territory with respect to limits. Okay. So now I can push my limits. So if I do limit here, the limit as n tending to infinity 1 by 2 power n plus 3 is going to be simply 0 by 1 plus 3 into 0, and that is just 0, right? So notice what I did. I just took this guy and then divided by this. I used my age-old division by the largest term here, so that I go into this familiar world of zero limits, finite limits, as opposed to some infinity here and claiming 1 by infinity is 0 and all that, which is a bit okay, which is also okay. I think a lot of people would be okay with that kind of an argument, but this is maybe a slightly cleaner argument to get to the result. So let's look at 5 now. 5 looks a little bit more confusing. Let's try that. 2 power n plus 5, limit as n tending to infinity. What did I put here? 5 times 3 power n plus 7. Okay. So now you have this situation where numerator is flying off to infinity, denominator is also flying off to infinity, and you have this infinity by infinity situation, and you have to sort of resolve it, figure out which one is going faster. Is it going to go to 0 or is it going to go off to infinity, right? So that's the sort of situation you have to resolve now, because the two infinities are not the same. One is like 2 power n, the other is some 5 into 3 power n. Okay. Of course, there's the plus 5 there, plus 7 there, all those things you have to worry about. So here again, we'll use our little trick of dividing by the largest guy around. Okay. So this little trick, as you see, is quite valuable. So which is the largest fellow, the big boss here? This guy is the big boss, right? 3 power n. So you can divide by 3 power n, and that's a crucial thing. Why did I decide to divide by 3 power n? And if you can try the other ones, you will not quickly get to the answer, but 3 power n will take you there. Okay. So this is important. So you divide numerator and denominator by 3 power n. When you do that, you will get this, and once you get this, limit is fine. So limit as n tending to infinity of 2 power n plus 5 by 5 into 3 power n plus 7 is 0 plus 5 into 0 plus 5 plus 7 into 0, whatever, and that becomes 0. So you see, as you could have guessed, right? So 2 power n is not going that fast. 3 power n is going much, much faster. It just pulls this limit down to 0. Okay. But this is like a neat way in which you can sort of divide by the largest guy. So divide by the largest guy, and then everything goes under control, and then you can do it. Let's look at 6. 6 is also like a similar problem. You've got 3 power 2n, 3 power n, 3 power 2n, 2 power n, etc. Let me write that down. Should remember all the constants there. Limit as n tending to infinity 3 power 2n plus 5 into 3 power n plus 7 divided by 7 into 3 power 2n plus 2 power n plus 6. Okay, so what would you divide by? Divide numerator and denominator by the biggest term is this guy, right? So you divide, it's there on both sides, numerator and denominator. You divide by that guy, you're going to get 3 plus 5. What is 3 power n by 3 power 2n? It's 1 by 3 by 3 squared, so 1 by 3 raised to the power n plus 7 into 1 by 3 raised to the power 2n. Okay, so this is just some exponentials and how those things behave. And then, so maybe if you don't like the 2n here, you can make it 1 by 9 raised to the power n. Okay, so hopefully you see that, right? So 1 by 3 raised to the power 2n is the same as 1 by 9 raised to the power n. How did I get that? So this 2 can go inside, and then that can work out. 7 plus, I'm going to get here 2 power n by 3 power 2n. I'm going to write it as 2 by 9 raised to the power n plus 6 times 1 by 9 raised to the power n, just to have an easy form. Okay? So even the other forms are okay. Now I'm ready to take limits. So if you take the limit, this guy will tend to, so this is another way to write it. You can say this tends to 3 by 7. Okay, all the other guys go off to 0. So you see how I'm able to handle these kind of expressions also when you have 2 power n, 3 power n, etc. The numerator, denominator. So you see in this case, this one actually goes to a finite limit, the 6th problem. Okay, now we're going to come to our interesting recursion territory. You see there'll be a lot of interesting problems here. The first problem sort of looks familiar. It's like a root problem. The one thing that I will find harder to prove for these kind of problems is monotonicity and boundedness. So what I'm going to do, at least for the purpose of this class, is to sort of assume monotonicity and boundedness, maybe calculate a few guys, convince myself that it's monotonic bounded, and then see if my limit calculation will work. Okay, so here is the recursion. What is the recursion here in the 7th problem? The recursion is an plus 1 is 0.75 times an plus 1 by an cubed. Okay, so this is the recursion. So supposing limit were to exist, and is finite, I'm going to get L equals 0.75 L plus 1 by L cubed. Then this will come off to this side. So I'm going to get 1 by 4 L equals 3 by 4 L cubed, or L power 4 equals 3. So L is 3, 1 by 4. So that's the limit. This I think should be true. You can check that. This would work. Okay, so the gap here in the argument is just the monotonicity and boundedness. Typically, you can assume that maybe you'll get something, but it needs to be checked. Okay, so this question, maybe you can assume that it's been given that it's monotonic and bounded. Okay, so we'll be careful in the way we word such questions. So here is another question. A1 equals 1, an plus 1 is 0.5, an plus 2 plus 1. I'm sorry. So even here, maybe for this one, it's simple enough. I'll try and argue why it should be monotonic and bounded. I'll show you how it's how I would do it for this problem, the 8th problem. It says a1 is 1, and it says an plus 1 is 0.5 an plus 1, right? So what do I want to argue? Let's say I want to argue monotonicity. Okay, so how do you prove monotonicity? So okay, first thing is compute a few values. Okay, so what is a2? A2 is going to work out as 1.5. What is a3? A3 is going to work out as 0.75, 1.75, and so on. It appears to be monotonically increasing. So can you claim it's monotonically increasing? So for monotonically increasing, I need to show an plus 1 is greater than an. Okay, so this is my way in which I write this. I'll put a question mark to say that I really don't know if this is true or not, but I'm going to assume it's true and see if I get a contradiction. If I get a contradiction, then it will work. So the other way to write it is this is true if, right? So an plus 1, so you can write it as we have an plus 1 greater than or equal to an if you write, instead of an plus 1, you write what its formula is, greater than or equal to an, okay, which is true if, so inequalities you can manipulate much like inequalities, much like equalities, except, for instance, this 0.5 an can go to this side with a minus sign. All of that is okay, except when you multiply by negative numbers, be very careful. When you multiply by a negative number, the inequality will reverse. Okay, that alone you have to remember. And other than that, most of the things are okay. Okay, multiplying, dividing by negative numbers, you'll be careful. But otherwise, its inequalities are just like inequalities, just like equalities when you manipulate. But notice what I'm doing here. We have an plus 1 greater than or equal to an. If this is true, I've not yet shown whether an plus 1 is greater than an. I'm just saying manipulate, manipulate, manipulate. See if the inequality becomes something nice. So if this is true, if 1 is greater than or equal to an minus 0.5 an, which is 0.5 an, which is true if, other way, writing this 0.5 to this side, 2 is greater than or equal to an, or an is less than or equal to 2. Okay. So, as long as an is less than or equal to 2, I am going to have an plus 1 greater than or equal to an. Okay. So, it is going to be monotonically increasing with 1. With 1, it is going to be increasing 1.5, 1.75, etc. Now, that I have shown. Now, all I need to show is this boundedness, right? I have to show this boundedness. If I show an less than or equal to 2, then I am done. Okay. How do I claim an is less than or equal to 2? You can do recursion, you can do induction. Okay. So, I am going to claim, so how do you do induction proof? So, you see a1 equals 1 is less than or equal to 2. Okay. Now, you assume an is less than or equal to 2. Okay. And then an plus 1 you assume. So, this is my induction assumption. Okay. You assume this, I do not know if it is true or not. I am going to do an plus 1, which is 0.5 an plus 2. If an is less than or equal to 2, this is going to be, I am sorry, plus 1. This is going to be 0.5 into 2 plus 1, right. This is going to be less than or equal to, because an is less than or equal to 2, this 0.5 an plus 1 is going to be less than or equal to 2, and that guy is actually 2 again. So, if an plus 2, an is less than or equal to 2, this implies an plus 1 is also less than or equal to 2. Okay. So, this is my induction hypothesis and getting an plus 1 to be less than or equal to 2. My initial condition a1 is 1 is less than or equal to 2, which implies a2 is less than or equal to 2, which implies a3 is less than or equal to 2, which implies a4 is less than or equal to 2, and so on. So, hence we have proved an is less than or equal to 2. Okay. So, I just wanted to show you a quick flavor of this, not a properly well written proof, but still you can see the argument and the main essence of the argument. I have shown you that this a1 equals 1 and an plus 1 is 0.5 an plus 1. That sequence is monotonic and it is bounded. It is bounded above by 2 and it is also monotonically increasing. So, now my MCT will apply. If my MCT applies, I am going to have L equals 0.5 L plus 1. It comes to this side, so I get L equals 2. Okay. So, think about what I did here. I mean, you could do this part. So, this part, you know, I'm not going to assume that you have a lot of training. You may have, some of you may have the training, but some of you may not have. Whether you have training to do this kind of proofs or not is okay. You can even do this graphically. You can just make a few plots. You will see immediately that this is monotonically increasing, and at least graphically to the extent that you can, and is bounded by 2. This is something you can see, and you may be able to guess the limit here and then prove it using MCT that this works. But if you can do these kind of proofs, then you are on much more solid ground. Okay. So, think about it. It is a skill maybe that you want to pick up. It is a little bit more difficult, but maybe it is interesting to some of you. Okay. So, that is that. Okay. Let us look at 9. 9 is a slightly easier problem. Okay. So, you are going to see here that it is a1 is 1 and an plus 1 is an by n plus 1. So, let us try that. Let us try 9. a1 is 1, an plus 1 is an by n plus 1. Okay. So, this will be much easier to show. You can show that this an plus 1 is less than or equal to an. We have, you can compute a few values. I mean, I'm not bothering to compute. A2 is 1 by 2, A3 is 1 by 2 by 3, which is 1 by 6, etc. So, it seems to be monotonically decreasing. We have an plus 1 is less than or equal to an if an by n plus 1 is less than or equal to an, and that you can cross, an can be cancelled because it is all non-zero, which is true if n plus 1 is greater than or equal to 0, which is true, right. So, this is always true. So, we have monotonic property. And now, boundedness is also very easy. You can easily claim an is less than or equal to 1, right. So, it is bounded, it is monotonic. I am sorry, I need more, like an greater than or equal to 0, because this is monotonically decreasing. So, it is decreasing, bounded below. Okay. So, this is a very obvious statement that an is non-negative. So, MCT applies. So, once MCT applies, you can do a limit. You can take limit on both sides. I am going to get L equals L by, okay, I have to be slightly careful here. So, let me do this. Limit as n tending to infinity a n plus 1 equals limit as n tending to infinity, let me write it carefully, limit as n tending to infinity a n by n plus 1. So, this n plus 1 is important here. So, notice what will happen here, I will get L here for this limit. What is going to happen to this limit? So, you have to be very careful. You have to put limit as n tending to infinity, and then this limit a n you replace by L by n plus 1. Okay. So, notice this is important. The reason why this is important is, so do not drop this n plus 1, this n plus 1 will still be there, right. So, once you have this, you can see that the situation becomes a little bit better. So, you have limit as n tending to infinity L by n by 1 plus 1 by n, and that equals 0. Okay. So, you get L becoming 0. So, notice the subtle bit of argument here when this n also shows up explicitly. I can push the limit inside, but then I should still keep this limit here. I mean, I can't get rid of this limit because the limit still applies, because the n is still there, not like n has disappeared. So, n is still becoming large, but I know the numerator is converging to this L, so I can put the L there and I will get my n plus 1. Okay. So, this once I have this L by n, L is finite. So, L by n is going to go up to 0, this whole thing is going to go up to 0. Just a quick argument to show how to work with this taking limits on both sides of recursion when n is around. Okay. But even otherwise, maybe you can argue that this limit will be 0 quite nicely. Okay. So, that is the MCT for the question number 9. Let us see question number 10. Okay. Question number 10 is very easy. I am going to do very quickly here. A1 is 0, an plus 1 is an plus 5, right. It keeps on increasing. So, you see 0, 5, 10, 15, 20, so on, and this is a arithmetic progression, the positive difference. This is not going to converge, right. It is not going to be bounded. So, this is not bounded. So, MCT will not apply. Okay. So, the 10th question, 10th problem, MCT will not apply for you. Okay. So, that is that. And then the 11th and 12th are quite interesting. I want to show you what happens to 11th and 12th. It's the recursion is the same, but the starting points are different. So, let us see what happens to this 11th and 12th. 11th, maybe I will do 12th here. The same recursion, an plus 1 is 2 an squared, an plus 1 is 2 an squared. However, here I am going to start with a1 equals 0.4. If you do that, just try a few values. What do you get for a2? 0.4 squared is going to be 0.16 times 2 is 0.32, and it is sort of decreasing, right. So, you will have a3 will be even further down. You can calculate it. What is 32 squared? It is 0.1024. So, it will be 0.2048 and so on, right. So, it's falling, right. So, here if you start with 0.6 on the other hand, notice what is happening here. A2 is 0.36 times 2, which is 0.72, 72 squared. If you do that, you're going to get something which is like 0.51. Maybe it will be close to 1, something slightly lesser than 1. A3 is some 0.98 something. Okay, so check it out. I'm just doing a rough calculation here. 0.98. It seems to be increasing. Okay, so in this case, when you started with 0.4, it was decreasing. When you started with 0.6, it was increasing. And that's one of the properties of the recursion. So, you see, if you want to check the boundedness property, we have an plus 1 less than or equal to 2an squared if less than or equal to an, I'm sorry. If 2an squared is less than or equal to an, okay, and then you bring an to this side, you see that an, 2an squared minus an is less than or equal to 0. Writing things all over the place. So, you can pull an out, 2an minus 1 is less than or equal to 0. Okay. So, this if you assume an is positive, okay, if an is positive, you can cancel this out. So, you get an is less than or equal to 1 by 2. So, this is all if you assume an is positive, which is true, right? So you get an is less than or equal to half. So it is a decreasing sequence if an is less than or equal to half. By the same token, you can argue it's an increasing sequence if an is greater than half. Okay. Now that's the first and crucial property. So this 0.4 is going to be decreasing, and it is bounded below. Okay. So this guy is increasing and it is unbounded. So this is sort of easier. This is going to go to a limit of infinity. Here the limit you can use MCT. So by MCT, limit exists, and you're going to get L equals 2 times L squared, and you can solve for this. You're going to get 2L L. So the thing is, I don't know if L is going to be 0 or not, right? So it's bounded below by 0. Okay. So I don't know if L is 0 or not. So I should bring it to this side. So L times 2L minus 1 equals 0. So it says L could be 0 or half. Okay. So clearly, you know, half is ruled out. Why? Because it starts at 0.4 and it's decreasing. There's no way it's half. So the only possible value is L equals 0. So the limit is in fact 0 in this case. Okay. So here you have a situation where the limit is infinity, the limit is 0. So even though the recursion is the same, the starting point matters. Okay. So be a little bit careful about the starting point. You can use the same sort of method. So notice how you can do this graphically. I would urge you to do this graphically. You can check that in one case it will quickly blow off to infinity, in the other case it will go down to 0. This is a wonderful recursion and an example of how to use MCT and try and analyze recursions and try and prove. Okay, so this is the end of this lecture, slightly long lecture, but I hope you learned a very interesting technique of analyzing recursions and other sequences. Thank you.